All right. Sorry for the wait, and good morning to everyone. For today, we'll be talking about analysis of variance or ANOVA. Sorry, can you hear me, class?
Yes po, sir.
Okay, thank you. Thank you, sir. All right. ANOVA is, or also known as Fisher's analysis of variance, basically is a method for determining differences between at least three sample means. Okay. When you're dealing with at least three samples or three groups of samples, you can use ANOVA. And what we're doing here is we're just basically trying to see, all right, how it's basically used to determine the effect of a certain explanatory factor relative to a response. For example, in this chart here, we're like comparing viral net levels or plasma nets. Plasma nets are like certain compounds found in the blood of a person. Okay. And therefore the plasma nets are like the response, okay, of a person when they are or rather they have plasma nets which can vary depending on their status of infection. All right. At least here we're trying to see whether a viral infection can affect the amounts of plasma nets a person has in their blood. Okay. Therefore, you can see here that the virus is our explanatory factor or suspected explanatory factor or the suspected cause, and the plasma nets is the sort of the effect or the response. Right. Now, when should we use ANOVA? We can use it as long as the response variable or the effect that we're trying to measure is numerical. And and of course, as long as we can pinpoint a sort of explanatory variable, we can definitely use ANOVA. Okay. And another plus with ANOVA is that it can handle a large variety of experimental factors. Of course, that includes repeated measurements of the same experimental setup, like for example, measuring before, before, during, and after a certain treatment or a certain event. Sorry, I'm having a cold. Now, there are also many types of ANOVA. Mainly have the one-way and the two-way, and there's actually another three-way ANOVA. And basically, it's easier to understand one-way ANOVA by imagining it or phrasing it as a one-factor ANOVA. Okay, I think a one-factor ANOVA would be a more appropriate way to describe it. All right, for example, we want to evaluate three different fertilizers, which is basically the explanatory factor here is the type of fertilizer. Okay. And our cause is the effect, or rather our response is the effect of the fertilizer on the crop yield, or how much crop can we harvest, okay, after applying the fertilizer. Okay. And in here, since we have like three different fertilizers, so we actually here have more than two groups, or more than two sample groups, and we can definitely use ANOVA in here. And since there's only one causative factor, namely the type of fertilizer, so you just have this is your causative or explanatory variable, the type of fertilizer. You can also definitely use one-way ANOVA. Okay. In brief, one-way ANOVA is about analyzing just one factor. Okay. Eh, now, when you add a second factor, okay, for example, we want to see how the type of field, okay, like the soil type, actually affects the crop yield. Okay, so for example, you have a farmland or field in the mountains, or a farmland or field in the floodplains. Okay, so in here, the factors are type type of field and the type of fertilizer, right? Therefore, this situation here already considers two factors, and this is what we call a two-way ANOVA, or like the two-factor ANOVA. And that's actually a lot more complicated when you're adding additional factors. Basically, because of course, first you're already dealing with two factors here, and there's a potentially third factor that may arise, which is basically the interaction between the fertilizer and the field. Okay, so it's not really straightforward or a linear analysis, because as you introduce additional factors, you also have to account for the actual interaction between the first factor, the first causative factor, and the second causative factor here. Right. Now we will jump to the example problem. Of course, we will be using R, using via the R Studio. Actually, my R program is having a bug or a problem. It's not really starting properly, and I think it's related to the local data of the R. If you're having a similar problem with R, you can just browse documents and look for a file related to R, like R history. You can just delete this one because it's just messing up the the startup of the program for some reason. All right, if you want to follow the examples, you can also download the handout for this lecture. I think I uploaded a actually, I can just send it through chat. That would be easier. Sorry. So if you want to follow the coding exercise, feel free to do so. All right. Now, ANOVA is quite a relatively complicated topic for me. Therefore, we're gonna have like I think two examples for today. And the first one will be about plants. Sorry about that. But the second example will be about carbonates. So at least you have an example that is about geology. Right. Our first example problem is about determining the effect of a chemical treatment on the weight of a plant. And we'll be using a built-in R dataset to conduct a one-way ANOVA test. Right. Of course, when you're doing a statistical test, we always have to state first the null hypothesis, or usually it's also known as the hypothesis of no difference. Okay. And we can basically just state that the null hypothesis is that the population mean of the control group is just equal to the population mean of the treatment group 1, and is also equal to the population mean of the treatment group 2. Okay. Or basically, we're just stating that there is no difference between the mean weights of the plants subjected to treatment, including the control set. May term dun, control setup yata. Sorry. Anyway, I'm quite disoriented. And then the null hypothesis is that not all the means are equal. Therefore, at least, or rather, for the null for the sorry, for the alternative hypothesis, for the alternative hypothesis H1, we're basically saying that at least one of the means are different from the rest. Right? And we can proceed first with first checking the data before doing the actual ANOVA analysis. And before that, you will need certain packages to be able to manipulate and plot the data. On okay. First is the DP layer package. You can just copy this one. We're first gonna install the DP layer package in our it's working. All right, sorry. So later. So sorry, I think I changed the theme of the R studio. So you can also actually just change the theme of your R studio program for your visual preference. You can just go to tools, global options, and then here you can just change the visual theme. Okay, if you're having an eyesore, or I don't know if it's gonna help you. You can like try out different themes for the program. Yes. I think this was the theme that I used. All right. All right, now let's install the DP layer package. Okay. Install that packages, open close parenthesis, and then quotation marks DP layer. And okay. So when it is successfully sorry about that. Yeah, when the package is successfully installed, you will see a prompt here that the DP layer is successfully packed and define some check. Okay. You may see a different message because I actually already installed the DP layer. Okay. But you can basically just see this result. Now the next step is to access the built-in tutorial data. Okay. In actual in actual or real world analysis, you will have to import your data, of course. But for now, we will just use this built-in data called plant growth. Okay. So you can just actually just call this variable. This is actually a built-in variable that contains a data set. So when you type plant growth, you will see a list of values showing weight and then a group. Okay, so you have a numerical weight and then you have your group. So you have a control group and then you have a treatment one and then treatment two. Since we're gonna manipulate this variable, we will have to make a copy of this one and then store it in a variable called my data. You can just type my underscore data and then just store the value of plant growth in my data variable. And then you can just call again my data just to make sure that it was properly stored. All right. Now this is just another optional way to view your data, but it's really just a trivial thing to do. Okay, but okay, first we use the set.seed function and includes 1, 2, 3, 4. Set seed function will just generate a set of random numbers. And you can specify a code like 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, so that you can always replicate this set of random numbers in the future. But anyway, for now, this is not really an important step. You can just skip it later when you're doing the exercise. And then we can just type this TP layer sample n my data command. What this command is doing is you're just trying to see the excerpt of the data. This command is useful when you're trying to view a data that has like 1,000 or 500 or a lot of Sorry about that. Where were we? Yeah, this DP layer sample in my data is useful if you have a data set that has like 1,000 data points. So instead of like viewing manually the whole list of data, you can just tell sample underscore n to show you like 10 representative or random data points from your data. Okay, so let's try this one. DP layer sample underscore n my data. Then my data is the variable containing your data, and then 10 is the number of data sets that you want to see. Uh-huh. So you can just try and play around with this command, like put in 3, you will get 3 data points and so on. All right. Um, you can also look at the levels or basically the categories of your data set. For example, here, your your categories here are under the group column. And basically you have 3 categories: the control, the treatment, and the treatment 2. Okay. Right now, it's easy to see that you have 3 categories within the group because your data set is relatively small. You only have like 30 data sets. But of course, when you're dealing with much bigger data sets, like 1,000 data sets, it becomes a lot more complicated. So you can just use this command levels, and then you just have to specify the variable containing your table data, and then the column, okay, indicated by the dollar sign. Okay. This group is just referring to the where is it? It's just referring to the group column in this my data table data set. Okay. So let's try to run this command. Okay. And you can see you have 3 categories. Okay, the control, the treatment 1, and treatment 2. And then if your data is not sorted, okay, later on in the analysis, you may want to sort your data according to the category so that you can do a more straightforward analysis. In here, you can use the ordered command. In the ordered command here, what we're doing is we're just specifying that that we will sort your data by the my data variable using the group column, and then we will arrange the data by this following sequence: first the control, and then the treatment 1, and then the treatment 2. Okay, and then we will store it back again to the my data group variable. So you can try running this one, and then you can call again your my data. So there's actually no effect here because the sequence here is just control, treatment 1, treatment 2, which is just the same as the previous one. But of course, just for the sake of exercise, you can just try to rearrange the categories here. So let's try showing treatment 1 first, and then treatment 2, and then the control group. Okay. Then we call again my data. Not working. That's weird. Hmm. Unexpected. Anyway, we'll just go back to that later on. Okay. Now, let's proceed to the summary statistics. This again is just for the purposes of having a grasp of the numbers, okay? Or just a summary of your data. First, of course, you'll be using here some functions from the DP layer module. So you have to first activate the DP layer library. So you can activate it by calling the library DP layer. Okay. And you will see a message like this one, warning message, package DP layer was built under our version 4.3.1. So that's good. And then we can sort of call this type this command. Okay. It has two parts. First part is we are telling R to group the data rows by the column group. Okay. What we're doing here is we're basically splitting the data into the category sample categories. Okay. So we have the control, the treatment one, and the treatment two. So instead of having like a big list of data, we are virtually splitting it up into the three different um three different into three different tables. Okay. After that, we have this symbol. You have your percent and then your greater than symbol and then percent. This is what we call the pipe function. This pipe function is basically a command that tells that basically passes the result of this one into the next command. Okay. So if you're familiar with Bash or Linux command, it is similar to the I think the end symbol. But anyway, what this command is doing is just it's passing this result into this command so it can further process your data. So after you have separated your data into three groups, we will process them using the summarize function, which will basically give you the summary statistics of each data set. And we have specified these three summary statistic parameters. You have your count, which will just count the number of data sets per group, and then you have your mean, which is basically just the arithmetic mean or the average. And you have to specify here the weight, the data column that you will be using, which is the weight data. And then na.rm is simply means or indicates that if there's an invalid or no data value, we will remove it. We will not include them in the calculation. SD is a standard deviation, which is calculated using the SD command. And still, we are still using the weight column. Okay, so we have specified it here and then true. Okay. So you've noticed that we're not using the dollar sign anymore in here, okay? Because basically you're already accessing directly the variable in this command. Okay. Now you can just copy paste this command, including the comments, okay, and it will just run fine. So you can just highlight this one, including the comments, and just copy it. Okay. So you can also try deleting the comments just to have a cleaner code, and you'll basically get the same result. Okay. So this is just the same here. Hmm. Control. Okay, it was quite rearranged. So let me rearrange this first again. Okay. So you have these results, which is just the same as in here. First column is your group, which is basically just the category, okay, or the sample group. Okay. And then you have your count, which is the number of data sets per sample group, and then the mean value of the weight, and then the standard deviation of the weight. Okay. Okay. Um, right. All right. Now we can further visualize our data. Okay. So you can just install the ggpubber package. You will use it later on for plotting data sets. Okay. And this is gonna be the output. Sorry, can you have like a 5 minute break? So we'll return on 8:12. Okay. So let's just have a five
Okay
minute
po, sir.
break for now. Yeah, thanks. All right. Sorry for the extended break. Okay. So I think we can. Okay, sorry for that again. I think we can resume now. All right. If you're done installing ggpubber, you will see this result. Okay, successfully unpacked and MD5 sums checked. Now let's try plotting the data as a box plot. Okay. Again, you have to activate your ggpubber module for you to be able to access it. Right. And you will see this message. Okay. And then we can now plot our data using the ggboxplot command. Okay. And basically what we're doing here is we're telling the command to use the my data, okay, as the input data. And then the x-axis will use the group, okay, group column, okay, and then the y-axis will use the weight column. Sorry. And then we're also specifying, actually there's a cleaner way to show this this code. So we can just basically just sort of rearrange this one. Color palette order y label x label. Okay. So this in here, you can easily see the sequence of parameters set in this command. You have your data that's gonna be used. This is the data that's gonna go in the x-axis, and then for the y-axis you will have your weight. And then for the color will be based on the group types. Okay. So the color will be color coded according to the group category. So you have a different color for the control, different one for the treatment one, and a different one for treatment two. And then you have your palette color. These codes are just signifying colors. Okay. So you can see later on, or you can just use normal color names like red, blue, green. And then the order is just the sorting of the plots. And then, yeah, we can just get this command, get this boxplot command, paste it. Okay. And you can actually just edit the colors here. You can put in red. You can put in lavender. You can put in sunrise. I know, no color for that. You can put in aqua. Nope, it's blue. Okay. Hit enter and you'll see a lavender is ugly. Let's change the color. Let's try magenta. Brown. Right. You have now a box plot. Right. And a box plot is basically just a plot of this middle part is the median, or the if you're gonna order or line up your data, this is the center value, the median. And then these are the extreme values. Okay. And you'll notice that at the brown dataset or treatment one, you have dots here. These are actually outliers or extreme values. Okay. And then you also have, okay, so just to formally introduce you to box plots, okay, this is your minimum, this is your maximum, minimum, maximum. This is the first quartile, or okay. First quartile, it's basically the median for the lower half of your data set. Okay. And then median or the second quartile, this is the by order, this is the middle part of your data set. And then the third quartile is this one. Again, the third quartile is just the median of the upper half of your data set. And you can just do a bit of reading here. The control group, this one, you can see here that the median and the third quartile are quite close together. So you have a clustering of your data towards a bit on the middle higher part of your data. You also have really high maximum values. And then for treatment group one, you have third quartile and the median in the first quartile. Basically, they're evenly spaced. Okay. And they look like a normal distribution. And they also have some outlier or extreme values here. And then for treatment group two, your median and the first quartile are quite close. So you have some sort of clustering here. And then you have like a spread of the maximum values. Okay. But we're gonna discuss this in detail probably in other lectures. You also have your mean plot. Okay. For the mean plot, right? Sorry about that. Where were we? All right, for the mean plots, again, we can just make a mean plot of the data set. Mm. We can do this by using the ggline command. And actually, again, we can just sort of format this to make it more readable. Right? So again, it's quite similar to the box plot. The only difference here is you have to add this mean standard error and the jitter. Okay. And then okay, the jitter is basically the connecting line here. And then you have your weight for your Y label and then your treatment for your X label. Again, I'll just enter this command in R and we'll get this result. Okay. I'll just discuss this later on the second example where we have a more detailed discussion. But anyway, in general, this plot is actually a bit more preferable when you're looking at a data that would be subject to ANOVA. Basically, ANOVA is a test that relies on standard error on variance and the mean. And variance in turn is related to the standard error. Okay. So this plot is actually a bit more um logically more related to the ANOVA test, but we're gonna discuss that later on. All right, let's proceed to the actual ANOVA test. In here, we'll be just using the AOV function to do the analysis of variance, to the one-way analysis of variance. So what we're doing here is we're just calling the AOV command, and then we're just telling it to. So this parameter here, the weight. So the first part or input in the AOV command is you have to specify the response variable. So this is basically the effect, the weight. And then the control variable or the causative factor is this second input parameter. So the group or the treatment done on the plant. Okay. And then the other input here is basically what data are we going to use. So I just specified here the my data variable as the input data. After that, we're just storing the result in this variable called res.aov or result of the analysis of variance. Now, this dot is actually it's just for naming conventions. Okay? You can just use a single word variable. It doesn't matter. So this dot is just for the sake of organizing your variables. So if for example you have a group of variables like result AOV, result mean, result SD, you can format it like that. Just so just just for the sake of organization. But for now, you can just use a single word variable or whatever. It doesn't matter what name of variable you use for now. Now after that, so you just input this command, and you can actually call the result by typing res.auv, and you will get these numbers. All right, I think it's this one. Just to quickly explain, or yeah, I think no, actually I have a slide for that. But basically, just to get a glance of this result, you have your sum of squares. Okay, so basically, this is the differences between of the data or the yeah basically the differences of the data versus the mean, and then you just have to square them each and then sum them together. So that's your sum of squares. Your degrees of freedom is to make the long story short, this is just the number of samples or number of categories minus one. I'm gonna just expound that later on. You have your group. Okay, so you have basically a sum of squares per group. Okay, and then a sum of squares for the residuals. Wait a minute, I'm running low on battery. All right. Sorry for the technical difficulties. All right. All right. For the group, what we're doing here is we have a sum of squares for the group. Okay, what we're doing here is we're actually taking the average or the mean of the values per group. For example, we're gonna take the mean of the control sample values, and then we're gonna subtract it from the overall mean of all the samples to get the variance for the groups. Okay. And then for the residuals, what we're doing here is we're actually um taking the mean of for example the control sample, and then we're gonna subtract the measurements, individual measurements, okay, from the control. Okay. And then we're gonna repeat that process on the treatment and then on the other one. Okay. So but the gist of it is that for the group, we're just taking the sum of squares or the spread of the data in between the general categories. For the residuals, you're taking the sum of squares within the groups. Okay. Okay. So this part is actually accounting for the actual variance between the sample groups. Okay. So this one is dealing with the actual question whether one group or one sample is different from the other. This residuals column is actually dealing with the errors or variances that are attributed with the actual sampling process. Okay, for example, you went to a mountain to do some rock sampling, and then for some reason you're unable to get fresh samples for all the rocks. So that's one possible source of error if you're, for example, doing some geological measurements. Okay. Well, for the group is here is basically if you're doing sampling on different areas and you happen to sample on a different geologic formation. Okay. Now for the degrees of freedom, you have in for the group degrees of freedom, you only have three categories: the control, the treatment one, and the treatment two. For the group degrees of freedom, you just have to get the number of categories minus one. So you have three categories, you just subtract one, you get two. For the residuals, it's quite a bit more different. You have to get the number of all the samples. In our data set, you have a total of 30 samples. And then you have to subtract one. And then you also have to subtract the degrees of freedom of the group or the sample degrees of freedom. So you get 30 minus 1 minus 2, you get 27. All right. All right. Now, after that, actually, this result is actually not really useful yet. Okay. There are further calculations that you have to do to be able to do the analysis of variance. So instead of manually calculating them, you can just use the summary command. The summary command is a special command in R that can summarize your ANOVA test and loads of different results. So this is our result, and I think this is just the same as this one. All right. I think I'll just go to the next slide. We have a detailed explanation here. All right. DF is your degrees of freedom. Okay. Sum of squares is basically the mean minus the data point value, and then you have to square them, and then you have to sum them. This one. And then mean square is just the mean square is also the variance or the spread of the data. This is just the sum of squares divided by the degrees of freedom. So for the group, your sum of squares is 3.7 divided by 2, you will get 1.8. For the residuals, your sum of squares is 10 divided by 27, you'll get 0.3. The F value or the Fisher concentration value is the ratio of the variances. Right? This is just talking about the variation between the sample means versus the variation within the samples. So in the ANOVA or the analysis of variance, what we're doing is we're trying to compare the different samples or the different groups of samples, and we're trying to see if they're actually different. Now, it's possible, of course, you will always definitely get different means because naturally samples or measurements will always have a variance. But what we're doing in ANOVA is we're trying to factor in the variances. Okay. If, for example, your two samples means are have a really, really big difference in the means, such that even if you account for the variance, they are still far apart, then you can say that they are two different animals. Okay, just what we did in the testing of the mean. In the testing of the mean, we're trying to compare two means, but we're not literally comparing the two mean values, but we're actually comparing their variances. If their means are far apart, and if the variances are actually quite far apart, you can say that these two means are different. Now, in the analysis of variance, you also have to account for the difference or the variance within the sampling process. Okay? So if you have like a data set with a lot of sampling variance, it might be slightly harder to see if the two samples are quite different. Okay? But if you can see that the variation between the samples are bigger than the variance or the variation within the samples, then you can say that the samples are significantly different. Okay? Such that you can say that they are two different things, okay, or three different things. Now, when you have a high value of F, okay, this will also mean that the variation between the sample is bigger than the variation within the samples. Okay, so it means that the samples are legitimately different, or the sample groups are, or the groups are legitimately different. Okay. Now, the higher the variation between the sample means relative to the variations in the samples, the higher the chance that the difference between the samples is not due to sampling errors, but due to their inherent differences. So yeah, they're legitimately different. And generally, when you have a high F value, will also tend to have a lower corresponding p-value. For the calculation of the p-value, I'm not gonna discuss this anymore. It's a manual process of looking up table values. Anyway, this is already being done automatically in R anyway. So let's just focus on the data. Now you also have another value here called the p-value. Okay, so which you can determine once you have known the f value. The p-value is basically if the p-value is lower than our chosen level of significance, we can reject the null hypothesis and conclude that at least one of the samples are different. Okay, so at this point we are rejecting the null hypothesis and accepting the alternative hypothesis. Now, let's say in this example, you want to be correct 95% of the time. So we can actually pick the 100 minus 95, the 5% or the 0.05 significance level. This one. This one. Okay. Now, since the p-value is 0.0159, which is actually smaller than 0.05, we can choose to reject the null hypothesis and conclude that at least one of the samples are different. Right? From this point, we can conclude that one of the samples in the plants, okay, the control sample, the treatment one, and the treatment two, one of them are actually different. Okay. But ANOVA is not gonna tell you which one is different. It's just telling you that at least one of them are different. One of them is different. Sorry. All right. You can also notice that there is a asterisk symbol in here. And this is just indicating that you can reject the null hypothesis here at this significance level. Okay, so if you're getting 3 asterisks, it means that you can reject the null hypothesis at 99.9% significance level, or basically you have like you can make a decision that will be correct 99.9% of the time. Okay. All right. I think I'll just proceed with example problem number 2, which is about carbonates. Right, carbonates. Suppose again this example is taken from the Davis textbook. Okay, but I just in the Davis textbook again, as usual, the solution is I think done by hand. But for this lesson, we're doing a R-based solution for the problem. Now, suppose you have obtained 5 pieces of calcite cemented sandstone. So this is 1, 2, 3, 4. This is actually 9. But yeah, sorry for that. It's a stock photo. Each of the 5 rocks in our collection is lithologically somewhat different. One has coarser grains, another has clay, third is slightly ferruginous, and so on. Now, for some reason, I don't know why Davis. What is the reason of Davis? But for some reason, we wish to determine if the carbonate content is same in each. So the question is, do these 5 carbonate samples have statistically the same carbonate content? Okay. And again, we're going to use ANOVA for this problem. Right? Just and I have a video of an HCl test. Okay. So I'm pretty sure you're familiar with this test, this HCl acid test. And it's used to determine whether there is a carbonate present in your rock or mineral sample. Now, you can determine the carbonate content of your rock using that principle. You can do a sort of geochemical test to determine the carbonate content of each rock by subjecting it to acid treatment. So we're basically submerging the sample in acid and then measuring the weight loss. Okay? The idea here is all the carbonate will be dissolved after you submerge the sample in acid, and after you weigh the sample again after the acid treatment, you can determine how much or how much weight was removed from the sample, which will correspond to the carbonate content. Okay. And since we only have like 5 samples, and for some reason we were unable to go to take replicate samples in the field. One approach is we can try just breaking apart the rock into fragments. Okay, so one sample you divide it into 5 or 6. And you hit it with the hammer and break it into replicates. And the purpose of that is you can determine the variability of weight determinations within each specimen. Okay. And of course, if the variation within the replicates of a single specimen is large compared to the differences between the specimen, the differences will be difficult to detect. Okay. So hence the ANOVA testing. And this is just a um this is just the data that we're gonna use. You have your samples, you have 5 carbonate samples, and you have 6 replicates each. Okay. What we're doing here is just to help you see or appreciate the problem. We're just trying to basically the causative factor or the explanatory variable is the type of the rock that you have. Okay, you have a sandy limestone, you have a clay limestone, you have an iron rich limestone, and so on. And then the response variable is basically the carbonate content. Okay, so we're trying to see here whether the type of the rock has an effect on the carbonate content. Okay, so of course, as a geologist, okay, you're quite familiar with the degree of cementation and the degree of carbonate contents. You can probably guess that of course the type of the sandstone or type of the rock will have an effect on the carbonate cement. So at least the ANOVA, for by doing the ANOVA, we're just trying to put our guess into numbers. Okay. So we can determine later on whether they are significantly different even even after accounting for the variances, okay, due to sampling and so on. All right. Um okay, so I have here a quite more detailed explanation. This table is what you call the ANOVA table or ANOVA process table. Okay? But for this slide, we're actually it's already filled up, no, for the with the details from the problem. Okay. So this ANOVA table is partially filled up with details pertinent to the carbonate problem that we're dealing with. You have your source of variation, you have your sum of squares, you have your degrees of freedom, and then you have your mean squares, and then your F-test. Right. Your sources of variation, of course, among the rocks, of course, the rock type that that will give you a potential source of variation, though you're not sure if it's big enough to introduce a variation in the carbonate content to be or to produce a statistically significant difference in carbonate content. You also have a source of variation, basically the replication error within the samples. The physical process of breaking up the sample into 6 pieces, into 6 replicates. Of course, the sample can get contaminated, or you might end up getting a piece of rock that is more weathered than the other, and so on. And then the total variation, of course, you have to is about the variation that accounts for these two. Now for the sum of squares, all right. Again, among the rocks in here, what we're doing is we're just taking the mean of the all the samples to get the grand mean, and then we just take the mean of, for example, the sandy limestone, and then we subtract it from the grand mean, and then take the sum of square for that sandy limestone. And then after that, we do the similar process for the clay limestone. We take the grand mean, all the samples, and then we take the mean of the clay limestone, and then take the sum of squares, and then sum all of them together to get the variance among the rocks. For the replicates, we are just basically taking the mean, for example, the mean carbonate content of the sandy limestone, and then we subtract the value of one replicate, and then we take then we square it, and then we do it again with another replicate until we get all these the all the sum of squares for the sandy limestone, and then we do it again for the clay limestone, and so on. Okay. All right. For the degrees of freedom for among the rocks, you just have to get the number of the categories. So in our problem here, we have like 6 samples, 5 samples or 5 categories. So 5 different types of sandstone or 5 different types of limestone. We subtract by 1, so you will get 5. For the replicates, you have like n minus m. So you have like 30 minus, sorry. So actually this is for 30 minus 5, you have like 95. Oh, 30 minus 4, so you get 26, sorry. Okay. And then for the mean squares, you just divide the sum of squares by the degrees of freedom. And then for the F-test, you just divide the variance among the rocks by the variance within the replicates. Okay. All right. In this problem, we actually have to import a data. And this is actually the data set taken from the website of Davis. Okay. Davis, I think, is a member or a staff of the Kansas Geological Survey. You can try looking up the university, this institution. It's really interesting because Kansas Geological Survey technically is a geology department within Kansas University, but they are also acting as a geological service company. So in the Philippines, you can imagine, for example, Mapua Geology Department that acts as a academic institution while at the same time acting as like MGB. Okay. So I think this institution has produced a lot of interesting technologies in geology, including some stuff in geophysics. Okay. But I'm not teaching geophysics, so we can discuss that. So anyway, you can get this data from this website. Okay. And I have actually uploaded the CSV and the text and the tab delimited version of the data. So I actually recommend that you just use the CSV data, CSV data for easier importing. So what we're doing here is we just have the read.csv command, and then we're just specifying the file path here. So we can do this from scratch. Okay. So I'm just gonna navigate to my data set, one ova.csv. You can just sorry. You can just control shift, right click, and then you can click the copy as path so that you can copy the whole path to this file. Okay, so I'm gonna paste it here. Just delete the extra quotation marks. And then for R, since R is a rather archaic language, you have to actually double the I think I'm not sure if this is I think forward slash. You have to double it because this slash is being used as an escape character. Okay. So once you have specified the path to your file, you also have to add additional commands here. Set header to 2 so that the command will actually read the header. And then you also have to specify the column classes. This is very important. I'm basically saying here that the first column, the carbonate content column, is a numerical column so that you can import this column as a number column. If you don't specify this properly, R will treat this column as a text, as a string, or as a text column. It will not read this data as a number. And then I'm also specifying that the second column is a factor. Okay. So a factor is sort of a identifier. This is sort of the identifier column. Okay. So I'm gonna copy this code and try to import the data. So for some reason, it's actually working, but just for your benefit, I'm just gonna show you some common errors. Okay. When you're importing data and then you haven't properly put in your forward slashes, you will get this unexpected symbol. Okay. So you can get this kind of error when you're not putting enough forward slashes. Or if you have an incorrect path, it will still proceed, but you will not get the correct value. Unexpected symbol. Huh, not working. Hmm. I'm not sure how to troubleshoot this. I just start R. So let's try that command again. So this is the variable name where we are storing the CSV data. This is the path, and then header to column classes. Let's see if it's working. I hope it works. Hmm. I'm not sure why it's not working. So we get this error. Okay. So what I did is I just had to retype all the quotation marks. Okay. This is one of the issues when you're trying to copy code from PowerPoint or from Word. The problem is you have a different quotation mark when you're doing it in R versus when you're doing it in Word. Okay. So or PowerPoint. So for some reason they're not compatible. I don't know why. But anyway, if you're having the problem that I was having earlier, you can just try retyping the quotation marks. Right, so this is our sample. Okay. First column is carbonate content. This is supposed to be percentage symbol, but for some reason, R fucked up the import, so it's just two dots now. Sample is your sample number. So you have like, I think this is supposedly your sandy limestone. This is your clay limestone, ferruginous limestone, and so on and so forth. Now we can try sorting the data, but since you can see here that the data is actually pretty well sorted already, so we can skip the data sorting part. The next part is calculating the summary statistics. First, let's activate the DP layer program. Okay. And then again, we just use this pipe function. So again, we're just grouping the data here by the sample column. So what will happen is you will take this data, this table data, and then you will separate it by the sample number. So sample 1, 2, 3, 4, 5. And then you will pass it to this summarize command. Okay, so not gonna explain this any further because we did it earlier. And from there, you can easily see the summary stats of each sample. So we have 6 replicates per sample. And you have a mean ranging from 17.7 to 19.9. And you have a standard deviation of around 2 to 3. Now, again, you can also do the box plots. And you have to activate first the ggpubber module. And then we can just we can just input this command again for this box plot. The x-axis is the sample group, y-axis is the carbonate content. Color will be based on the sample type or the sample ID. And then the palette, we will be doing a color coding, blue, yellow, red, green, violet. And then we will order the plot as 1, 2, 3, 4, 5. And then these are your labels. So there's an error, unexpected input in the sample CaCO3. So you can see here, it's this time R is actually putting a different color for this quotation mark. So we can just correct it. And notice that the code is now clean. Okay. And then you have this box plot now. Okay. So you can see here that generally you have a similar spread of data. Okay. So this length of the box is the indicator of the spread. Okay. So more or less they have a similar spread, probably except for sample 5, which has a relatively short spread of data. You can also do a mean plot. So I'm not going to explain this one any further. Okay. So again, note that ANOVA depends on the mean and the variances, and also which is in turn related to the standard error. Hence, the scatter plot with mean and standard error bars are a closer indicator of the ANOVA test. You can see here that the mean and standard error here are all overlapping. more or less they're all overlapping except probably for sample 3 and maybe even sample 5. But this is just an initial assessment, of course. But we can suspect early on that you might have a different sample in sample number 3. Okay. All right, for the results, we can do now the ANOVA. So we just use the AOV command. Again, this parameter is the response variable or the effect variable. In this case, the effect is the calcium carbonate content, and then the causative factor is the sample or the rock type. Okay. And then the data, of course, is our carbonate contents rocks variable. We store it in this carbonates results variable. And then we just run this analysis. And we can call it. Okay. So this result is basically the same as what you will see in the Davis textbook. Probably I think there's just a slight difference in the degrees of freedom. I think the RDOF is a bit more conservative, okay, because it subtracts more DOF. It subtracts an additional -1 for the residuals. Then we can summarize the results so that we can get a complete picture of the AOV. So we have your degrees of freedom here, then the sum of squares, and then the mean square. And then the F value, which is just mean square of the sample divided by the mean square of the residuals. Okay. Now you have this p value, which is equal to um, point uh you have like 4 zeros, so this is a very very small number. 0.0000511. Okay. So note, when you have a very very small p-value compared to a certain significance level, so if we chose a significance level of 0.05, this number is definitely smaller than 0.05. So we can reject the null hypothesis and say that the alternative hypothesis, we're gonna stick with the alternative hypothesis that at least one of the samples here are different. There are actually, so the ANOVA will not tell you which sample is different. It's just telling you that one of these samples are suspicious. Okay, that's all. If you want to determine which sample is different, you can do other testing like the Tukey test. But I haven't made the lecture for that yet, so I'm not sure if I can still discuss it. But yeah, that's basically what ANOVA is gonna tell you. One of them is suspicious and is probably different from the rest. Okay. So you can't say yet which one is different. Okay. Now you notice that you have 3 asterisk marks here. It means that you can actually reject the null hypothesis at 0.001 level. So if we reject the null hypothesis here, we can say that we will be correct 99.9% of the time. Okay, so we are more or less freaking sure with rejecting the null hypothesis in this case. All right. All right, so that is the second problem, and as we're nearing the conclusion of the lecture, I'm gonna give you a parting gift, which is the problem, which is the exercise. Okay? We will just have one problem, which is about zeolites. And basically, we'll be talking about the origin of the zeolites and their potassium contents. And in theory, the chemical composition of a mineral will depend on the thermodynamic conditions of the during its formation. So different temperature and other chemical stuff will influence your chemical composition given the same mineral. For example, zeolites, they're basically silicates that form at low temperatures, which is either during diagenesis or like diagenesis is like the post-depositional processes, or maybe even low-grade metamorphism, like your hydrothermal vents or hydrothermal conditions. They also can form as hydrothermal vein deposits. Now you're given a Hewland dot text, okay, for your exercise. And this will give you like 92 samples of Hewlandites, okay, which is known as a common zeolite. And you have your percent potassium contents. Each specimen has been classified as either sedimentary or hydrothermal in origin. Now, our job here is determine whether their potassium content are significantly different. Okay? Actually, I'm not sure if this is. Wait. Actually, I'm not sure if this is appropriate because there are only two samples. So I'll try opening the Huron Diets dataset first. Huron Diets. So let's import it first. Read.delim. And then I can just add the path. There's the Huron Diets. Huron Diets. Huron. Let's copy the path here. Copy as path. And then paste the path. And then add the double slash. And then you have to specify the data types. So we can open this text file first. Sorry. Actually, I think you just have two data sets here. Okay, so this is your numerical and this is your factor. So I can put header true and call classes numeric factor. This works. Hewlandites. But anyway, I think you just have two types here. You just have your hydrothermal and sedimentary. So I think I have to change the problem. So scrap that human rights problem. I will just instead use another data from Davis. Just do a variance. All right, I think I'll just upload another exercise. Okay, so I'll just probably scrap the previous exercise. So for now, I will delete this exercise. And I will just edit. Please wait for revised handout. All right. So far, do you have questions regarding the lecture? I'll just upload a new handout. Okay. That will actually need a ANOVA testing. All right. So that basically concludes the lecture for one-way ANOVA testing. So after this lecture, I'll try to upload as soon as possible the revised exercise and the revised handout for this lecture. If you have no questions, you can either just ask them later on. Okay. All right. So if you don't have any more questions, I think we can end this class already. Thank you for participating.
Thank you, sir. Ingat po.
All right.